So yeah, we know this titanium alloy is widely used in different industries, such as aerospace, automotive, and also medical industry. But here we are focusing still in the design of a turbofan. The idea is to reduce the casing of the fan for a special case of certification, which is the containment test, blade containment test. So to simulate this turbofan, we need to know really well the mechanical properties in different directions: compression, tension, shear, plane strain. So it's a very complex material. We have published the complexity of this material to predict the elastoplastic behavior and damage. Also, you can use non-conventional material as a nano indentation. So you can check this result in this publication. But well, to predict accurately the design of a turbofan for a containment test, we will need elasticity, very well predicted, initial yielding, hardening and damage, and also the fracture, right? So for elasticity, the material has shown to be quite orthotropic, and for initial yielding also. For hardening, we see a directional hardening, which is quite complicated also. And for damage, we have many options, like micromechanical based damage, or we can just use a low a fracture criteria or damage criteria based on Johnson-Cook, for instance. So this is the approach we are trying in this work. Only isotropic law, Cook law, von Mises for initial yielding, which is easy. Johnson-Cook, which is quite easy, but still have some complications. Johnson-Cook is a strain rate dependent and also temperature dependent. And for damage and fracture, also we have a strain rate and temperature, but the triaxialities will affect the fracture strain. So we analyze this from different tests performed like 10 years ago for our strain rate testing and temperature testing. So we see the material in stress strain behavior is quite different. So for this, we have to take into account the identification of first the plasticity, which is already done using neural networks, and also the damage. So for Johnson-Cook plasticity, we will have three factors: hardening depending on strain rate, and also the third factor, hardening softening, thermal softening. Though there are many parameters to identify. One approach is to identify at one strain rate and one temperature is you perform several tests with notch, so tensile tests with different notches. So you will have different stress triaxialities. So those are the points in the graph. And for different triaxialities, the sample fracture at different strain. So you plot this, and then you try to adjust the Johnson-Cook, which is the dashed line. These results have been already published in Aerospace in this year. And here we identify all the parameters, which is damage, these parameters, D1, D2, until D5. We predict quite well the experiments. So we assume, but we still have some, some inaccuracy here, and we have zones we don't see so much. So we'll see if it works for this application. So first we model the turbofan with different boundary conditions, different meshes also. We perform sensitivity analysis of the results. So we try to reduce the size of the mesh here in this zone of the case, because the impact of this blade, which is detached in a blade containment test, will impact this zone. So we'll try to predict the fracture, the fracture shape, and in case if there is a fracture. The idea is not to have it. Yeah. So the preliminary results are compared with those are not our tests. It's performed by big companies, but we can compare the simulation when the blade is detached and touching the casing, the turbofan, the outer shroud, and also when the blade is impacting the second and the third blade. So it's quite similar. It's the only way we can validate our model. But now, as we consider the model is quite correct, we can compute the stress field during the impact. So in this case, we perform a simulation with a very high velocity, which is not real for the operation of the turbofan, but just to see how it will deform and fracture the case. So we can take stress, the strain field, triaxiality, and also we can predict damage. So which is the parameter between 0 and 1. So when it's 1, the material breaks. We compare now the identification of the Johnson-Cook model with the prediction. So when we look at the predictions, we can extract from the software the triaxiality values on different areas. So the values are around 0.77 and 0.45. So we are more or less in this triaxiality range. So this identification really is not so important for our model, but maybe it could be for the blade. And now if we compare, this is the zone of interest. So in this zone, we really need to perform the testing to predict the damage in a turbofan case. Now, if we compare, we extract similar values, but not only stress triaxiality, we go to these points and we extract the strain, the equivalent plastic strain in this zone of the case. We can also compare in which area we are. And actually, we are quite far from the values we use for the identification. So this is a very important finding to the industry, so the aerospace industry, aeronautical industry, because when you perform testing, you should try to search for this area, which is difficult because actually triaxiality is not an average value; it's a very evolving value in a small sample. It's a very local value. So normally the triaxiality you have to compute it and identify with inverse identification to take the right value, but you also have to measure when the sample breaks, which is difficult. You just see a very brittle, quasi-brittle fracture. So what we did to the end, we are still working on it. We vary the damage parameter. What if we identify D1 and we perform an error of 5%? What is the effect in the equivalent plastic strain? So we can see what 5% of error in D1 is more or less 5% error in the plastic strain. So conclusions: local stress triaxiality field near the fan blade affect the identified damage models. So we are quite close for stress triaxiality, but for fracture strain, we still have to work on it. Also, variation affects 5% variation affecting the same grade, and other parameters are under evaluation. So I will show you really fast some sensitivity analysis we are still performing. This data was sent last night. So what we are doing, we are varying each parameter of Johnson-Cook model, plasticity, 5 parameters, and damage, 5 parameters also. We are in 5% variation. We'll see what is the variation in the blade damage in case damage, which is the damage is the value which related to fracture. So when damage is 1, it will fracture. So here we perform the simulation with the real velocity of the turbofan, and we reach a damage of 0.5. So you still have 0.49 of damage to reach fracture. So this is the last part of the presentation, and also we investigate rotational speeds, different rotational speed, how it will affect the design, and also we have to determine a term for the safety factor, which is not here. We cannot do it as elasticity reaching yielding. We are predicting the fracture. So how much plastic deformation we consider, or triaxiality we consider, to reach the maximum value, which is fracture, which is failure, real failure for the operation. Those are our last results. So thank you for listening.